Okay, so now we're looking at epoxides. Epoxides are a type of ether. Specifically, they're ethers where they're constrained to a little three-membered ring. So it's a cyclopropane with an oxygen in it. And these things can typically have lots of substitution on them. So I could have lots of different carbon chains flanking this. It would not be an issue. These are called epoxides. Sometimes you'll hear people refer to them as, oh my goodness, oxyrines. Okay, I call them epoxides. Let's take a look at how to make them. So, we'll call this synthesis of epoxides. So we'll look at how to make them, and then we'll look at what we can make with them. And this is pretty standard for, I don't know, how to think about the different functional groups, right? There's two different sides to it. One is how do we make them, and the other side is, well, what can we make with them? And if you know both those things, you can implement them. If you know those well, at least, you can implement those in some sort of synthetic scheme. So some of the stereochemistry and stuff for epoxide gets pretty wonky with the stuff you can make from them, but generally the other reactions for them and stuff aren't so bad. I think the hardest thing for a lot of students is just to get used to the three-membered ring. It just looks weird. Yeah, so what do we use? So if we want to make an epoxide, we can make it in a single step from an alkene. So you notice that it's syn. Epoxides are almost always syn because it would be difficult to, it would have a lot more strain if you had it going from the front bond to the back bond. It would be a lot more difficult. The reagent that we use to convert that over is something called MCPBA, which stands for metachloroperoxy, as in peroxide, but peroxybenzoic acid. So the term meta, and you'll learn about this next semester, but just so the word doesn't seem like it's coming out of nowhere. So metachloro, I can write that down too. So generally when you see it, it's written as MCPBA. It stands for metachloroperoxy. Start a new line here, benzoic acid. And so the peroxy part is referring to this. The peroxy part is referring to this part here. That's a peroxide. So we know that hydrogen peroxide looks like this. So that's what the peroxy refers to. And the acid part, benzoic acid, is referring to the fact that this is a carboxylic acid and it's attached to a benzene ring. And then metachloro is just telling you that you have a chloro group meta to the peroxybenzoic acid, which is telling you the position on the benzene ring, which is a whole thing you'll learn about next semester. But yeah, this is what that reagent looks like. So generally, there are other reagents as well that can be used to make epoxides, and they're all, at least when you're doing it in a single step, they're all different flavors of peroxides. So this is just a really common one. You'll notice, as I said earlier, that the addition here is syn. It's syn addition to an alkene. And yeah, you can imagine, if we looked at the mechanism for this, it would be clear why it's syn. But you can also just imagine that for a three-membered ring, it's already pretty strained. Like this is a pretty strained thing. Like what are the interior angles of a triangle? Yeah, they're usually add up to 180 degrees. So these, for an equilateral triangle, that'd be 60. What's the hybridization of that carbon? It's sp3. So what do we want those bond angles to be? 109.5. So, you know, if this is 60 degrees, you can imagine that there's just a lot of strain in that. If you think of strain, actually, let me into more detail on that. So if you look at just like cyclopropane, which is what I've drawn here, and this sort of explains what we're going to look at in a second, which is why these things are so reactive. So ethers aren't very reactive. Alkoxides make bad leaving groups and all this kind of other stuff that we learned about in the substitution elimination reaction. But epoxides are very reactive, and so we can kind of think about why that might be. So remember that for cyclopropane, what's going to be our interior angle here? It's going to be right around 60 degrees because this is a triangle and just the geometry constrains it to being 60 degrees. We live in a world that's described accurately by Euclidean geometry, and that's just sort of what a triangle has. So what is this carbon here? Well, it's sp3 hybridized, so the ideal angle is going to be 109.5 degrees. So if the actual angle is 60 degrees and we think of strain, emails from the TA about our exam. If we think about strain as being deviations from ideal bond angles, then this thing is like really strained. When we're talking about steric strain, we're talking about strain of like maybe 4 or 5 degrees away from what the ideal angle is. This thing's going to be, over 40, closer to 50 degrees away from its obvious, from the ideal bond angle. And so these things have a lot of strain in them. The result of that is that they want to release that strain. So they're sort of high energy species. For a cyclopropane, there's not a lot of ways out of that. They're not, alkanes in general don't react very much. You could burn it, and if you did burn it, you would notice that it burns at, it releases a lot more energy than the equivalent, just like a straight propane molecule. So if you wanted to kind of get some pop in your gas tank, you could add cyclopropane or something through it. But for an ether, for an epoxide, if we're looking at a really simple one like this, that strain is still present, okay? And now that it's not an alkane anymore, we sort of have these other pathways that we can go on to open it up. And that's what we're going to kind of look at ultimately. So the unique, I guess the main takeaway from this is the unique reactivity of epoxides relative to ethers, right? The unique reactivity of epoxides stems from strain in the three-membered ring. So because these things have so much strain, because they're so high energy, they just turn out to be really reactive relative to normal ethers. Okay. So the other way you can make epoxides is to start with a halohydrogen, or a alpha hydroxy halide, or alpha, I don't know, whatever you want to call this thing. You start with a halogen and an alcohol on carbons that are right next to each other. And then you can take this and just add in some base. You can take this and just add in some base and get this reaction to go. You might be able to predict this reaction if you've been coming along nicely in your mechanisms. What we end up making here is an alkoxide and we can see that the alkoxide is right next to an alkyl halide. So this part of the molecule here is very nucleophilic. And then we have this carbon here with a leaving group attached to it that is electrophilic. So it's similar to one of the other examples that I showed you. The molecule can just kind of react with itself intramolecularly. In the other case that I showed you with an alkyne, I think it was in one of the workbook problems or something, that was something we didn't want to happen. Here, this is something we actually want to happen. So you'll notice that it's attacking from the front, and the bromide's on the back. So you still end up getting the epoxide like this. You can't have a trans epoxide, so you shouldn't have something where this is on a wedge and this is a dash. If it's an epoxide, at least if you're looking at it from the top, if it's an epoxide, they both need to be on the same plane of the molecule they're attached to. Okay, so that's a way to do that. And remember that to make this, we know a reaction for that. We can use water and Br2, so another one of our alkene reactions. So I think when we went through alkenes, I was like, hey, these are really important, put these on flashcards. Hopefully you took me seriously, because yeah, we come back to these a lot. Come back to these a whole lot. So you get this. You'd also get the other enantiomer of this, plus. But that reaction is useful for that. But I would say overwhelmingly, at least in the lab, the way that we make epoxides is to use the first strategy, which is with using MCPBA. For obvious reasons, it's one step. It gives good yields. This other method is a little bit trickier. So yeah, so this step is SN2. All right, so let's look at the types of reactions we can do. Reactions of epoxides. So I'm gonna break these up by the type of reagent that we're using, and I might be able to finish it out in this video. I don't want to go on too long. Yeah, we're at 12 minutes. Yeah, we probably finish these in this. Let's start with strong nucleophiles. So let's start by looking at what happens when you have a strong nucleophile. So let's say I start out with my simple epoxide here, so the simplest one we can have. And I take and I react it with a very strong nucleophile. What do I get out of this? I just get a simple SN2 reaction. So this carbon becomes this carbon. And then so the weird thing here is that because the leaving group it leaves, right, but it's still kind of part of the molecule. So this bond here breaks, but you have this other bond on the other side that's still intact. And so the leaving group sort of leaves in the sense that the electrons leave with it. These electrons here were the bond that are in that lavender. Those are the electrons that were in the lavender bond. But yeah, it still actually stays part of the molecule. And this is part of what makes ether so useful. Epoxide so useful is that you can then take this compound on and do another reaction. So you sort of have now, this might not be super obvious because we're still kind of getting our feet wet with synthesis, but now I have this piece on the molecule. I can do another reaction on that if I want to. And we'll look at some synthetic strategies for that. Usually when you're making these, though, you don't leave them as the alkoxide. What you'll do in a second step is you'll add in something to get rid of the alkoxide. So if you're doing this type of reaction where you're using an alkoxide, you'll use the conjugate acid of the nucleophile when it's possible in the second step, and that avoids having any kind of unwanted side reactions. Like you're not going to get accidental nucleophilic displacement or something, and if you do, it doesn't really matter. But yeah, so generally the workup is done with the conjugate acid of the strong nucleophile. So workup just means that in the last step of the reaction, you do something simple that's like, I don't even want to say high yielding, it just gives you exactly what you want. So like I'm just doing some really simple acid-base chemistry here. So if I was running this reaction, I would start it out and like stir these things together and then like go to lunch or something. I don't know how long that takes. And then when I come back, I would just dump in some methanol to make sure I got it in the protonation state that I want, rather than trying to work up the alkoxide. Yeah, so I guess one thing to ask here is, one thing that's unusual about this that should maybe unsettle you a little bit is normally this reaction wouldn't work. And the reason is that, like, let's say, for example, if I were to say, take this and I want to react it with let's give this something different here. Let's say I take diethyl or ethoxide and I want to react it with this to do this reaction. We're not really going to see that go, and the reason is that methoxide makes a really bad leaving group. Okay, and that's why we went through all these different strategies for turning bad leaving groups into good leaving groups, because hydroxides, alkoxides, they're bad leaving groups. Usually you have to add acid or something to get that reaction to go. So that doesn't work. Why is it that this works for epoxides then? And this relates back to what I was talking about earlier, which is, okay, the reason, if you want to get down to the fundamental aspect of it, the reason that alkoxides don't typically leave as leaving groups is because they're so high energy. But here, the energy of or sort of the thermodynamics that work against you for the leaving group are compensated for because you're getting some ring strain relief. So when I break this bond here, so inside the ring of the epoxide, you've got all these non-ideal bond angles. Everything's kind of closer to 60, and you want it to be closer to 109. And so it's unhappy. So once it opens up, I get some relief and lowering of the energy of the molecule from that, and that compensates for the fact that I'm creating a kind of high-energy leaving group, that I have an alkoxide leaving. So this is an instance in which alkoxides or something that's equivalent to a hydroxide does leave. Okay, so you don't want to make the mistake of protonating this in the first step. And some students will do that out of habit, which is, up until now, has been a good habit, which is to say, oh, I know I need to protonate this in the first step, so maybe I have something like this happen. And then the CH3O minus comes in and kicks that up. Yeah, I mean, I can see why you might think this is reasonable if you're new to the subject, but you never have, we don't have very much methanol present in the first step. If any, basically we have none, right? Because we're using methoxide, so that doesn't exist, so don't make that mistake. But the other thing that you should note is we don't ever have a strong acid, which this is, and a strong base exist simultaneously in solution unless they're reacting with one another. Okay, so if methoxide is coming in to react with that epoxide, it's not going to do a nucleophilic attack. It's just going to take that proton away. So even if that reaction were to happen, it doesn't actually activate that towards nucleophilic substitution. The acid-base reaction would just happen in reverse. But basically what I'm saying is the main thing to take away from this, and this is a super, super, super common mistake that students make when they're first starting out, is don't do what are called mixed media mistakes, where I have a strong base, so I have a strong base and a strong acid present at the same time. That just doesn't happen, okay? You can't, it's just, I think we talked about this in a different video or in lecture or something. It's kind of like something being hot and cold at the same time. It's just not possible. One can't exist with the other there. They're sort of tied together through thermodynamics. Okay, so don't make this mistake. This is, I'm going to erase this and say, don't make that mistake. So what actually happens here is the epoxide just opens up, even though the leaving group is not that great. And the reason that it's allowed to do that is because it releases strain in the ring. Okay. So the nice thing about this, though, is that this reaction, this is an SN2 mechanism. So that means that all of the reactions we know from SN2 chemistry can be used to open up the epoxide ring. So any nucleophile, any strong nucleophile that we know from our chapter on substitution could conceivably be used to open up the epoxide. So if I were starting with an alkene and I wanted to do some chemistry on it, what I could do is convert it to the epoxide. And now I have this whole host of different types of things, chemistry I can do on this. So for example, I would use, if I wanted to do this, I might use MCPBA, metachlorobenzoic acid. But yeah, if I go and I take an alkoxide and then I work it up with the alcohol, what do I get out of this? I'll get an alcohol on one side. Oops. And on the other side, I'll get the ether. And you'll notice that the addition here are when the ring opens up, I guess the epoxide ring, that I see what I would expect from an SN2 reaction, which is the stereochemistry gets inverted. Okay, so all the rules that we learned for SN2 hold here. It just takes a little while to get used to the idea that this leaving group actually stays as part of the molecule, and that can be a little bit confusing, I think. Okay, another reaction we could do is we could use cyanide, which we know, again, is a really good nucleophile, and we could work that up with water. Oh, I should note that for all of these reactions, you're forming chiral centers here, and so these are all racemic. So you get whatever I'm showing plus the other enantiomer. Okay, but we get cyanide, and then the second step where you use water is there because it protonates the alkoxide that forms from the epoxide. I could also use SH minus and then work that up with water. Again, I get the alcohol. So this, just to be clear, this oxygen here becomes these oxygens. The nucleophile attaches to the other side. Let's see, I'll put some reactions in here that you haven't learned yet. One reaction that's fresh for you is if we want to get rid of, if you just want to take and open the ring up, but you don't want to, you just want to replace it with a hydrogen. You can use this reagent that you'll learn a lot about next semester. It's called lithium aluminum hydride. It's okay to just think about this as being kind of like just hydride. So sodium hydride would be the obvious choice if you wanted to use it as a nucleophile. It ends up working out that sodium hydride is not a good nucleophile. It always works as a base. So we have to use these kind of really weird salts. But the result of it is you get the addition of hydride. This is the reason why I'm saying it's okay to think about it this way. Fix the stereochemistry up here. Ultimately, what you end up getting is hydride addition. So lithium aluminum hydride looks something like this. And these hydrogens, when they go, when you sort of use them in a reaction, the electrons go with the hydrogen. So it's as if it behaves like this, like the hydride behaves as a nucleophile. But in order to get hydride to actually behave as a nucleophile and not as a base, you have to use these kind of jacked up reagents like lithium aluminum hydride or something. That's really the only thing that you have to know here. But yeah, the net result here for us synthetically is we get a hydride addition there.